All right, everybody. Well, welcome back to our third video here on section 2.8. Hopefully you got a chance to watch Ryan's first two videos. The first video explains the idea of Newton's method, and his second video explains the problems that can happen with Newton's method. Now what I'm going to do is show you some more advanced applications of Newton's method, starting here with example 3.8.10, where we're going to use Newton's method to approximate a solution to this equation, x squared minus sine of x, which can't normally be solved using algebraic methods. Now remember, in order to use Newton's method, we need to construct the equation such that the number that we're trying to find is going to be a root of a function. So the way that we're going to do that here is let's go ahead and we're just going to solve this equation for 0. So if we go ahead and subtract the sine of x here, we get that x squared minus sine of x is equal to 0. These two equations have the same solution set, and therefore we can choose our function that we're trying to find the roots of to be x squared minus sine of x, which is kind of similar to what we did when we were using the intermediate value theorem to figure out where things were positive or negative. But in this case, we're trying to find the roots of f. Now, to complete this, I need you to recall the equation for Newton's method. It's that our second guess, x2, is equal to our first guess, x1, minus f of x1 divided by f prime of x1. If you're a little bit confused about where this equation comes from, you should go back and watch Ryan's videos. Remember, though, this is just an application of tangent lines, and the equation has been reworked to solve for the x value in the tangent line equation. For this problem, we've already been given that our x1 is equal to pi over 3, so we have our first guess. Therefore, x2 is equal to that x1, which is pi over 3, minus the original function evaluated at pi over 3 divided by the derivative of that function evaluated at pi over 3. So that's where we need to end up. Let's do some of the intermediary calculations. Over here, let's calculate the derivative of f prime. So that's going to be 2x minus cosine of x. And now let's evaluate f of pi over 3 by plugging into the original function. So we get pi over 3 squared minus sine of pi over 3. And if we simplify this, we're going to get pi squared over 9 minus root 3 over 2. Not a super nice answer. And then if we calculate f prime of pi over 3, we get 2 times pi over 3 minus cosine of pi over 3. And if we simplify that a little bit, we get 2 pi over 3 minus 1/2. Now, we can plug in these two pieces of information to further simplify our guess for x2. So we get pi over 3 minus pi squared over 9 minus root 3 over 2, all divided by 2 pi over 3 minus 1/2. So let's take a look graphically at what we just calculated. If we take a look at Desmos, so far I've inputted our original function, and the root of this function is the number that we're trying to find. We're trying to find this number right here, 0.8767. So our first guess for our x1 value is this value here at pi over 3. And then what we're going to do is we're going to put a tangent line through the point pi over 3, f of pi over 3. And then our next guess is going to be where this tangent line hits the x-axis. So I've plugged in our answer here, and you can see that that is right where our tangent line of our first guess hits the x-axis again, and this is getting closer and closer. That's 0.9026. That's closer and closer to the 0.8767 that we're looking for. So even though we're just plugging things into an equation, what we're actually doing is we're using a tangent line to get our approximation closer and closer, and that's the idea of Newton's method. Now I'm going to switch back here and give you a few seconds to copy down the work if you didn't get that copied down. All right, go ahead and pause if you didn't get that, and let's move on to the next example. So for example number 11 here, we're going to do a similar thing where we're trying to approximate the cube root of 29, and we're trying to calculate it up to x3. So we're going to do 2 iterations of our guess here, and it's going to be a little bit more powerful than what we did with linearization in section 2.9. Now to approximate this root, we actually need to do 2 things before we apply Newton's method. First, we need to decide on what our function f of x is. The key here is that our f of x needs to have our original number here, the cube root of 29, as one of its roots. In other words, we need f of the cube root of 29 to equal 0. That's the function that we're going to be using to do our calculations. Second, we need to choose a good x1 value. And what I mean by good here is a value that we can calculate by hand. So in this case, we can do that before we do anything else. Our x1 here is going to equal 27.
Our x1 should be 3 here, not 27. And 3 is a value that's used throughout the rest of the problem.
And that's because the cube root of 27 is equal to 3, and that's what we're going to use as our x1 value. Now, let's hop back to our first step here. We need to decide on a function that's going to give us a 0 at our desired root. So, the way to do this is that we want x to be equal to the cube root of 29, and then if we solve this for 0, we're going to come up with our equation. So, we need to cube both sides. So we have x cubed is equal to 29, and then we need to subtract the 29. So we get that x cubed minus 29 is equal to 0. And now we've just decided that this function has a root at the cube root of 29 by design. So our function that we're dealing with for the rest of this problem is x cubed minus 29. Let's go ahead and calculate the derivative for that, because we're going to need that derivative in order to plug into our Newton's method equation. So the derivative is 3x squared. Now again, recall that x2 is equal to x1 minus f of x1 divided by f prime of x1 using the Newton's method formula. So let's go ahead and calculate our x2, given that our x1 is 3. So in this case, x2 is equal to 3 minus f of 3 divided by f prime of 3. If we go ahead and evaluate those functions, we have 3 minus 3 cubed minus 29 divided by 3 times 3 squared. If we simplify one more step, we get 3 minus 27 minus 29 divided by 3 times 9, or 3 minus negative 2 divided by 27, which is eventually equal to 3 plus 2 27ths, so a little bit bigger than 3, which we would think, because 29 is a little bit bigger than 27, so the cube root of 29 should be a little bit bigger than the cube root of 27, and this is our little bit of a correction factor there. So this is our first value, and I'm going to go ahead and convert this to a fraction form just so it's easier to plug into our next example. So that's equal to 83 over 27, which is in turn approximated by 3.074. And again, that is our x2 value. This problem wants us to go to x3. So let's repeat this example one more time. So we have x3 is equal to x2 minus f of x2 divided by f prime of x2, which is equal to 83 over 27 minus 83 over 27 cubed minus 29 divided by 3 times 83 over 27 squared. All right, let's go and separate these with a little bit of a line there. And this is actually the final answer that you would be able to use to put into WebWork to calculate x3. I'm not going to use this answer though to finish our explanation for this problem. Instead, I'm going to use a numerical approximation, and I am going to plug this into a graphing calculator to see how we could do that. Alright, so I have my graphing calculator here, and I'm going to use this to do Newton's method to get a really accurate answer. So what I need to do first to use Newton's method is I need to start with my x1 value, and in this case, that is 3. And then what I need to do is I need to plug in this Newton's method formula using the recursive function, which is this answer button, and then I'll be able to use Newton's method as many times as I want by just pushing the enter button repeatedly. So let's go ahead and do that. So I now want to take the answer of my previous function, which was a 3, and I want to take that number, this x1 value, and I want to subtract from it. We're going to do our original function, which is our first number, x1. We're going to go ahead and we're going to cube that number. So we're going to raise that to the third power, and then we're going to subtract 29. I'm using this function f right here. And then I'm going to take that and I'm going to divide. So I just did f of x1. So I plugged in my previous answer, cubed it, subtracted 29. I need to divide this by 3 times that first answer, x1 squared, which is my f prime. And if I hit enter here, I'm going to see that I get my 3.074. And now if I hit enter again, I'm going to get my second iteration, which is going to be the numerical approximation of this number. So what I just got is that my numerical approximation for x3 is 3.072. So I'm going to write that right here. This is approximately 3.072. And at this point, I could actually hit the enter button repeatedly to get a closer and closer numerical answer. And we see that actually, as we hit x4, we actually got within a close enough area that our decimals stopped changing. So we have 9 decimals of accuracy just by doing Newton's method 3 times. And that's all we're going to do with this problem. Again, the final answer that you need for Math 132 is that when we plug this in the third time, we're just going to plug in x2 back into our Newton's method formula, and that's all we can do without using a calculator like you'd normally be asked to do on a quiz or an exam. That's all we're going to do in this video. This is just the first page of these notes, so go ahead and watch the next videos, which will cover some more examples.